hello to everyone, and thank you very much indeed for joining this lecture hosted by the AES UK section. You're very welcome indeed to our monthly lecture, which today's all about taking an idea, and specifically a loudspeaker design concept, all the way from a sketch to something that can be reliably and repeatedly made on the production line. And before I formally introduce our two speakers tonight, a quick personal connection and recollection, if I may. Like a number of people in our audience tonight, I suspect I started my career at BBC Radio in London in studio, frontline maintenance and project work. And one of my first assignments was what was called Outside Studios, which was responsible for things like the Hippodrome at Golders Green, and more importantly, the Maida Vale recording studios. And my boss there was a very engaging chap called Pete Thomas. And he at the time was very busy with the loudspeaker, the monitoring loudspeakers in the Rock and Pop studio MV4, and was trying to get the Beeb to accept and install a thing which he called his BB5, I think it was, the Big Box 5 loudspeaker that he had designed himself along with a colleague, I think it was Adrian Loader. And that became, during my time at the Beeb, the monitoring speaker in MV4. So it goes back a long way, the PMC company. From that small beginning, of course, grew the world-renowned company. And so over 3 decades later, I blench when I think how long it is. It's a tremendous pleasure tonight to introduce our guest speakers, who are a PMC's principal R&D engineer, Toby Ridley, and Peter Thomas's son, Ollie. Ollie has moved over to the dark side according to his job title of commercial director, but his roots, I can assure you, are very much in engineering. He studied mechanical engineering at Oxford Brookes firstly, and then some electroacoustics at Salford. Started out in high performance automotive engineering with Red Bull technology, but saw the light, of course, and came back into the fold and worked in several roles at PMC, from R&D engineer to R&D manager, and then as commercial director latterly, bridging, as he puts it very aptly, the link at the top between product development and the market into which those products are going to be sold. And in his time at PMC, Ollie's been responsible for the design and development of the majority of their current product range. And he takes justifiable pride in having built up the engineering team that did all that work and designs now some of the finest loudspeaker systems in the world. And in that task, of course, he's very ably, more than ably, assisted by our other speaker tonight, who's the principal R&D engineer, Toby Ridley. Toby joined PMC, a classic route, actually, coming in as an industrial placement student from Salford, where he was studying audio and electroacoustics. And I suspect these are the words from his colleagues, and I'm sure they're more than justified, that he had an immediate impact with his passion for audio and his ability to apply new technologies and concepts to PMC's products. Toby now works on a vast number of R&D projects and guides the engineering team on acoustical principles of design. And thanks to his experience at PMC, he now is one of the world's leading authorities, if not the leading authority, on transmission line loading of loudspeakers. So that's all said and done. Welcome, Toby and Ollie. Over to you guys.
Well, thank you very much for the introduction, Mike, and to yourself and Sue and AES UK for offering us the time to present and talk today.
Could I just interject one thing I did forget to mention, and that was the question and answers. Sorry, got so enthusiastic about the talk. A small admin point, there is a Q&A button at the bottom of your Zoom screen, and we'd ask that if you have questions, and I'm sure there will be plenty, that you post them in the Q&A slot rather than flinging them around in the chat, because we might not see them in the chat. By all means, use the chat, but for questions that you want answered by the panelists, please pop them in the Q&A. And we will stay in the webinar for the Q&A sessions, because there's a manageable size of audience, and we'll go through you all and convert you to panelists so that everybody can join in a free conversation. Sorry, Ollie, I cut you off by the stocking tops there. Please, Toby, Ollie, the floor's yours.
No, that's quite all right. Thank you very much. So yeah, I think I'll dive straight in. So yeah, as Mike was saying, my job title now is commercial director, which fills me with resent every time I have to say that to people. I prefer to define myself as more of a technical director, and I am now kind of just responsible for all of the different engineering functions from R&D, product development, but also the production engineering, quality control, and our IT systems. Toby, I guess, yeah, if you want to intro yourself.
Yeah, well, again, thank you very much for the very kind introduction. I'm definitely not my words, but kind of you to say. Yeah, I've been at the company since 2018, I believe it was, where I was there on placement year, and I've never left. Ollie kindly took me back, and yeah, it's been an amazing journey, and a lot of learning, a lot of growth, a lot of experiences that I don't think you could get anywhere else. And yeah, I think hopefully we'll be able to talk you through some of what we do on a day-to-day basis tonight, and the job we're doing to bring these speakers to life.
Yeah, that's absolutely the idea. Is we wanted to run through sort of general product design and development as we see it and how we do it, and then also give more of an insight into that at PMC and our various sort of design procedures and facilities that we use to hopefully stir some thoughts amongst you. So PMC itself, I'll do a quick intro, and I've got a bit of a video to play too. But for those of you that don't know, we're a global designer and manufacturer of high-end studio and hi-fi products. As a company, we utilize our experience in in-house knowledge to offer more than just products to our customers, often getting quite involved with studio design and equipment setup. We see ourselves as a kind of all things audio kind of company. Toby, I'm going to rely on you to let me know if slides and videos are working good enough.
All good so far.
So we founded in 1991. We've always designed and manufactured our products in the UK. Shown just here in this quick video is our headquarters in Biggleswade in Bedfordshire. And we also have a manufacturing facility in both Luton and Sandvik. Ending there on a picture of our founders, Peter Thomas, as Mike pointed out, is my father, and his colleague that co-founded the business with him was Adrian Loader. Both of them were pretty obsessive audiophiles, super passionate about their hi-fi, and they were both working in the professional audio business. So Pete and Adrian pioneered the development of transmission line design speakers, addressing it to the professional market. They believed that the same loudspeaker could and should be used throughout the creative chain as well as in the home. And that's kind of one of those company philosophies that I think we carry through into our design nowadays. So I was speaking to Mike briefly before, and this is the first PMC system that was sold into the BBC and Maida Vale Studios for. And since then, the company's expanded, it's grown. We now design and produce products for hi-fi and the custom installation markets. But it's really the studio heritage that that we're most proud of, and that's what I think defines the company most, where we focus most of our efforts in terms of new product development. So this is just a quick shot of Capital Studios, one of the world's leading studios, which we're particularly proud to have our products in. And actually there's a sort of product development story to go with it, which is that what's shown here in the soffits is the QB1 PMC speaker, which we pretty much designed for Capital Studios. They were keen to have a super high-end replacement to what they had in there before. It wasn't something that we had a product offering, and so we just set about it based on that. Produced the first 2 pairs, which went into Studio A, and Studio B, and then we ran with it, and we've now had, I think, maybe 20-25 installations with QB1s and QB1 XBDs. Yeah, more recently, we've opened up a few of what we call PMC studios. They are our own studio facilities, and they're typically Dolby Atmos mix studios, but we use them as kind of a really high-end product presentation suite so that we can demonstrate in the best possible light our products. So the PMC design philosophy, I mean, we were founded in the belief that there were many ways in which loudspeaker design could be improved. That's why Dad made the the bold move to quit the BBC and produce his own loudspeakers. But ever since the beginning, it's like the innovation, the attention to detail, and working with music creators, which help us develop our own technologies and products, which we produce sound with the highest accuracy. Again, it doesn't matter whether it's a home audio model or a professional studio model, the same approach to the design in-house by the engineering departments, the exact same approach is used for both. And up on the slide in front of you is like the two key things for us is low distortion and wide directivity, two key like technical performance metrics that we strive to achieve better and better results each time we embark on a new product development project. So yeah, every PMC is designed and made in the UK. Every component is measured and recorded at every stage of production. And it's this kind of obsessive level of quality control which helps us ensure that every speaker that we manufacture is the exact same one as the last one, or sorry, the first one we ever made. So at the end of product development lifecycle, we end up with reference speakers, and one of them is representing the exact design goal, what we were trying to achieve. And we gauge and measure and compare every single speaker we manufacture from that point forwards against this design reference. So into product development itself. Nowadays at PMC, we are following quite a rigid structure for product development. As the company has grown, we have bigger and bigger engineering teams, and what comes with that is the need for this structure to make sure that everyone is working efficiently and coordinating in the right direction. You know, we want to capture all the requirements for a new product. We want to integrate any burgeoning technologies we may have developed through R&D, specifically what Toby is working on often, and then thoroughly test the product for reliability and get it ready for release. The big key phases of product development, which is fairly generic across any design manufacturing company, are these shown in front of you, which we've got the concept stage, product design and project planning, then the big part in the middle, which Toby, I'll hand over to Toby, and he's going to talk us through that in a bit more detail, the development process. And then towards the end, making sure that we get the product ready for manufacturing, test it, and then decide how we're actually going to launch it and release it. All key stages. So time scales wise for product development is something that we talk a lot about internally. And I think it's what a lot of people ask us is, yeah, how long does it take to actually design and develop something? And it depends on lots of different factors, on where we're starting out, how much time we have at like the beginning and the end, that concept stage, whether we're developing one product or a whole range, and then kind of some of the technical aspects of it, whether it's a passive speaker or an active speaker. What technologies might we want to try and apply, and where those technologies are in development. Some projects have like a theory from R&D we want to apply, but it's not really a design ready stage. So examples being different drive unit technologies. And we've got to a stage where we've got an idea, and then we've got to develop it and repackage it into a product that we are happy to be able to manufacture consistently. And I think what we're quite powerful at, or good at, is allowing a little bit of leeway to let some of the structure slide and slip if we feel like we're onto a really good idea. So an example of this is about 18 months ago, we released a new range of small active products, and within them is like a web-based software which can control the product. It's something that we don't have a huge software engineering design team in-house. And we didn't have a lot of this in-house knowledge, but knew that if we could develop what we had in our minds, what we had planned out in a concept stage, we knew it was going to add huge value to the product. And basically, we just really wanted to do it. So the beginning part of development was very much like learning some of these skills and ensuring that we could develop this software to the best of our ability. And it was worth putting that time in, stretching out the project and developing a better product. So concept stage. We normally have quite a lot of different concepts floating around. It's often defined by multiple product sketches, sometimes by hand, sometimes 3D modeled and rendered up in CAD. Also at this stage, we're trying to estimate some of the other specifications which will eventually form the product design spec. So yeah, this is an example of a hand sketch, and we've got like some of the details in there, such as heat sinks and how we're going to manufacture it, different processes and ideas associated with it. And then many months later, what fell out from this product sketch was the product in .NEF, which was our AML2 active monitor. This is from many years back. Similarly, this is another product. And like the hand sketches, the initial sketches were focused on the industrial design, the aesthetic, to get an idea of what the finished product was going to end up like. This being like an all analog, extremely high-end integrated amplifier. And then finally, an example showing how powerful like a rendered 3D CAD image can be, and getting an idea of what the product will look like, which for all the stakeholders in a business, it can be a very powerful tool, really good at capturing the imagination. So after we've decided on which concept sort of bears the most merit, we've got the design spec stage, which is definitely the most important part of any project. It's where we're trying to capture and define exactly what the product is, what we're going to set out to design, and maybe some of the detail into how we're going to go about doing it. The more detail, the better. A vast amount of detail goes into our product design specs. We want to ensure that we are not only making the right thing, but it's also a measure of our success of our design teams when we get to the final product, to compare how well we've done. And along the way, we'll need to make compromises, or we'll want to tweak the project, and we come back to this product design spec to make sure that we are doing the right thing and we haven't wandered off. And so again, this area of the business needs input from all areas. It needs like accurate market and sales information. It needs a really good understanding of how we're going to manufacture this product, probably many years before it will even go into manufacture. And actually, yeah, top of the list, we've got project name. So we tend to come up with a code name for all of our new products. And it can be a real mistake if you come up with something really stupid, because then that's just locked to the product for the next 2 years. But likewise, yeah, you don't really want to call it exactly what the product is, so we can keep a degree of secrecy. Other bits in there, and then we've got scope, description. Important just to come up with a really concise description of what we're trying to achieve here. What's the point of doing this? The market we're selling into, styling requirements, technical requirements, those are normally the easiest to define because everyone knows exactly what they want their new speaker to look like, sound like, what the features are. Then we've got like manufacturing detail, the schedule. Everyone wants to know the schedule. Sadly, costing, pricing, parts, including development costs. And then, yeah, but definitely the last bit, which is most important, approvals and sign off, making sure that everyone's bought into this process and agrees. So, quick example of a snapshot of a product design spec. We've got some of our concepts in there. We've got some of the approximate dimensions, and we've gone and found what we think some of the market opportunity could be. We've got some star requirements listed out, and we can kind of go off pieced a little bit here. Then we've got lots of technical requirements. We've got an idea of how we want to manufacture it, and we've thrown in some ideas, all of which will go completely off scripts, and we won't ever achieve those timelines or the technical brief.
A very good example of one with quite a silly product name as well. It's the Blue Baboon project.
Was that on these documents? I think it might well have been.
It was. Yes.
This was Project Blue Baboon. They were not Blue Baboon.
To the previous project, which was Project Pink Panther. So it was seemed fair.
Anyway, so this is the main bulk of product development. Really, is getting stuck into developing from our product design spec a product that we have at the end of it, which we can deliver and start manufacturing.
Yeah, I suppose to this section really is if we're thinking back to that sort of cone-shaped diagram you had, this is possibly the longest, well, definitely the longest stage of the whole project, but it's only one small section in that graph. It's the development and prototyping stage, but it is really the meat of the project. Sorry to cut in on you there, Ollie.
No, you're fine, go for it.
So yeah, I mean, it goes through several stages. A lot of these, although we're listing them in a specific order, a lot of them will be done concurrently with each other. We're always quite vocal about the fact that because we're doing transmission line design specifically, they can be incredibly fussy about the exact drive unit parameters that go with the cabinet. And the cabinet can be incredibly fussy about the exact drive unit that's with that. You know, they interact with each other in a complex manner and have quite specific requirements on each other. So we end up doing drive unit development and transmission line development, or ATL development, as we're going to refer to it, very much in tandem. So although they're in different sections, that's one that we have to cover together. Then obviously there's crossover development, and that's another huge process, drive unit development, for mid-range drivers and high frequency drivers, and that might include waveguide design, things like that, or even just aesthetic choices and prototyping mechanical couplings from one part to another. Once we've sort of gone through this very early stage prototyping, where we'd be creating very early stage prototype parts, we'll then get an initial prototype made, which will be to final spec, hopefully, and full visual quality and things like that. So it'll have the correct molded parts, machined parts, things like that, instead of prototype parts. And that'll get signed off on as an aesthetic design. And then it's onto packaging, final voicing, which would be a little bit more crossover development, just to make sure everyone's completely happy. And then, yeah, creation of marketing materials. And then, yeah, that's the sort of early prototyping stage done. We could possibly move forward there.
I'll just say, to give us an idea, that very first step was the project plan, and this is where our product development manager spends a great deal of time, and we pull on his understanding and knowledge to know who is doing what and when. We produce one of these lovely Gantt charts and schedules, assigning tasks to various members of staff, detailing the entire sort of timeline of a project. So what tasks are parallel and what need to be sequenced to stack up, and we can work from sort of the front end to the back end, or the back end to the front end, to figure out how long it's going to take and how quickly we can get that product to market.
So yeah, the next few stages, few slides, we'll be going through the first step of the product prototyping stage, which will be ATL development. So as it is the sort of core technology for PMC, it's very important that we get it right each time and improve on it each time we make a new product. So we spend an awful lot of time at the front end of every project working on this, as I say, in tandem with drive unit design. So the procedure we sort of go through this, it's not entirely rigid, but it's generally this route is some initial sort of back of envelope calculations. We've also got some spreadsheets and scripts that will do very rough calculations on transmission line length for what our target frequency is, various cross-sectional area calculations to give vague ideas of what we should be starting out with for a given drive unit parameters and things like that. From there, we'll go on to much more complex simulations using FEA tools like Console. We'll then create prototypes, following on from successful simulations, and then we'll start tweaking on those prototypes and go on from there. So if we go to the next slide, please.
Yeah, no, I didn't know if you wanted to talk through
about
not the images that we have in front of us. Some of our beautiful. This is, I think, what we call like an acoustic prototype. I don't know if we've already covered that, but yeah, where we've got an idea of the transmission line, the enclosure, how it's acoustically working, and some of the drive unit development itself. Of course, we wouldn't dare sort of show this to perhaps the sales and marketing team. It might well put them off on what our product's going to look like.
This is very much behind closed doors in R&D, these sort of stages are, because as Ollie says, marketing people tend to get a bit scared when they see an MDF box and think that's what we're going to be trying to get them to sell. But this is a very important stage where we have removable panels, so we can go inside the cabinet, play around, rip other panels out, move things around, and very much quickly iterate on the design, which is very important. We want to, if we want to make a change or need to make a change, we want to be able to do that as quickly and inexpensively as possible, so that we can push the design forwards. So you'll probably notice on these cabinets that you see in the image, there's no tweeter holes or anything like that. This is very much, we're getting the bass correct in the speaker, which is, the foundation of any loudspeaker really, is getting it's got well behaved and well extended bass performance. So that's the thing we always start off with in these designs. So
right.
So we've done initial calculations and say we'll move on to simulations in Console. So we use Console for a variety of different purposes. We'll do everything from high frequency drive unit simulations, waveguide design, to simulating entire cabinets with drive units in them to make sure that we're going to get roughly the performance that we expect from that cabinet design. So I've got a couple of example images here. One is just a sort of surface plot of SPL being produced from a quite extreme baffle profile of a tweeter. It's not something we are actually going to use or would use, but it's fun to try these things out because it's free to try it in Console. I think that's what's so amazing about having access to these simulation tools, is that you can try really outlandish things that even with rapid prototype today, you would still not want to waste time on necessarily trying, but you never know, it might work out and it might become something quite special. So it's worth trying some of these slightly rogue ideas that might cross your mind. Other examples we've got there is just it's actually a subwoofer design that we've on the sly produced to a few studios around the world, which is a very high performing 15-inch subwoofer. And it started off in Console simulations where it showed enormous promise, and we went from there and built some prototypes and ended up selling them.
The design process is kind of very much simulate something, prototype it, measure and test it, evaluate it, both with audio analyzer type tools and just listening, and then go back around, make some modifications, simulate again, prototype.
Absolutely. And what's quite fun, if we go on to the next slide, is that there's obviously, those of you who are quite well versed in acoustics should know that there's obviously frequency domain and time domain ways of looking at any acoustic problem. And Console lets us look at both of those domains in quite high detail. So this is now a time domain simulation of a tweeter moving in at 20 kilohertz, again, quite an extreme waveguide profile on there. But it enables us to see how the drive units are behaving over time and see the mechanical and acoustic interactions that would be going on in that system. So again, talking back to what the benefit of having access to these tools is, if we go back not that many years, it was almost impossible to run simulations for these things. So if you wanted to see how a design was functioning acoustically and get a really good in-depth idea of how it was performing and how the sound was behaving around a cabinet, you had to try and find a way of measuring it. So I'll pass back up to Ollie for the next few slides, which is quite an interesting project that we did before my time, which Ollie led, which is, you can go through here.
Yeah, sure. And the major reason I like to bring this up is I get to see acousto-optic laser-based interferometry, which is always fun. But this was some research that we did in conjunction with the National Physics Laboratory quite a lot of years ago now. They were sort of developing a technology, and they were looking for someone with sort of design and industry understanding and knowledge to be able to apply it. Essentially, what the measurement technique is taking a scanning laser device and shining it across the front of the speaker, not actually physically touching the speaker, but shining it through the air just in front of the speaker, off of a reflective board on the other side of the measurement area, and then recapturing the laser on its return. So it's a automatic laser scanning device, and it moves the laser through this kind of 2D plane sound field in front of the speaker, and is essentially measuring the time of flight of the laser. And if you shine that across the speaker when there's no sound playing and when there's sound emanating from the front of the speaker cabinet, you'll see a very tiny difference in the time of flight of that laser. And what that is the sound pressure in front of the speaker is causing a change in refractive index in the air. And it bends that laser light. It changes the length of the path that it travels by like a tiny, infinitesimally small amount, but it's able to detect it. So if we shine that laser at each point across this kind of grid in front of the speaker, and sort of sweep a sort of sine tone through the speaker, fully automated, it takes a while, but it can build up an idea of what the sound pressure is in front of the speaker, and we can produce images and videos similar to those which we can now simulate in console, where we can kind of see sound wave propagation. So this, what you're looking at in front of you, kind of needs a bit of explanation. The left-hand side two video screens are showing essentially kind of a comparable speaker from the top-down view, showing one with a very sharp-edged cabinet and one with a slightly rounded over cabinet. I'll play it again. We've got frequency and proportionally time average directivity. But yeah, just focusing on like the images on the left, you can take away from it a few different things, but you can very much see how the sound wave reacts to the edge of the baffle, and it shows a basic acoustic principle of diffraction. But we did use it as a useful tool to help direct us towards seeing what the impact was of some of the different geometries that we use in cabinet design and waveguides. But as Toby rightly pointed out, it's all completely out of date now, and we don't need it because we have powerful simulation tools which do it for us. And this was just us generating a 3D visual of incredibly limited resolution. But it's nice to literally see sound.
Yeah, it's quite amazing that you can actually visualize the sound waves. It's not a simulation, that's an actual measured thing, which is very, very cool. But yeah, it's nice that we can do similar things a lot cheaper now. Obviously, the benefit of this is you don't have to worry about the validity of it as much. With simulations, you're always very much focused on how valid is your simulation, is it accurate, and having to verify it against real measurements. With something like this, obviously, this is the real measurement, so there is that benefit. But yeah, the cost and the speed and everything is remarkably better with simulation tools, and we can just keep trying new things very rapidly. So back to simulation tools. When we're simulating an entire cabinet, the sort of data we can get out of that, we can look at predicted pressure or sound pressure level at different places all around the speaker, so we can place it in different acoustic environments, but half space, full space, things like that. We can see how the drive unit and the vent might sum at a certain distance at a certain angle and things like that, to check that we aren't getting any strange phase or likely to get any strange phase interactions between the two. We can look at the air velocity with it at any point within the cabinet, or outside the cabinet. We can look at driver excursion, electrical impedance. Taking it further, we can look at mechanical flexing of parts, so cabinet sides, see if there's going to be any issues with cabinet resonances or drive unit breakup modes and things like that. So that's super helpful to be able to get a good grasp of whether any of these things are going to cause issue or whether we're likely to hit our targets for these parameters before we've even cut any wood. So that's very handy. So obviously the most important thing, as I mentioned with simulations, is that you can verify that they're accurate. So the next step is to build a prototype of what you've simulated and make sure that what you can measure is indeed what you simulated. And that gives you obviously good confidence in that future simulations will also tally with reality. And also it means that we know that we built this prototype correctly, which is also a bit of a worry sometimes if it's being done by hand or in a rush or anything like that. Obviously, drive unit parameters can sometimes not be what you're promised. Obviously, we do measure these ourselves, but things can change. So obviously, measuring is extremely important. You need to know the reality of what your cabinet or speaker is producing. It lets us by iteratively taking suites of measurements and repeatable suites of measurements. It lets us compare different designs. We have two different prototype ideas on the go, or comparing against a reference unit. It lets us rapidly improve on our designs by make a small change, measure it, make a small change, measure it. And yeah, also to confirm the results of listening tests. I think obviously we've mentioned many things are our core philosophies, but one of our big core philosophies is that listening to our designs is just as important as measuring the designs. In fact, they're equally as important. So we never rely solely on either listening or measuring with any part of the design. So we are always listening, even if it's just as a base part of a cabinet, just a woofer in a transmission line. We'll be listening to that, be it pressed over or whatever.
Yeah, just to jump in and just expand on that, I was going to say that, our ears kind of capture so many different metrics and parameters of how you can measure audio quality, and they stick them all together in a far superior way than you can measure with a whole lot of different measurement equipment. You get there eventually, but your ears are capturing reflected sound and direct sound. They're capturing distortion, and they're incredibly sensitive. So yeah, if you train your ears properly, then they're still a useful tool. But hey, Toby, what are these graphs we're looking at?
So these graphs we're looking at. So on the bottom left, it's just some in-room measured responses of a few subwoofer prototypes and showing the comparative benefit of measuring. Obviously, we can very quickly overlay multiple measurements and see, this one has this much more energy at this frequency, but has other issues at other frequencies. So we can very quickly make decisions between things with good quality measurements. On the top right is something a bit more interesting. So this is a metric that we've sort of come up with at PMC, which is really, really helpful with trying to optimize our transmission line designs, and it's excursion efficiency measurement. So we're using a laser displacement sensor, which will be fired at the drive unit, and it's similar to previous the laser interferometry measurement. It's measuring propagation delay between the fired laser and the returned laser. So it's seeing how far it's traveled and sampling that at, I believe, 8 kilohertz our laser is. And so we're correlating that excursion of the drive unit with measured SPL at wherever we measure the SPL. So in this case, it's near field to the vent. So we're seeing basically how much output or how much acoustic energy are we getting out of the cabinet for a given drive unit excursion, and obviously measuring that across a sweep of frequencies. And that lets us really easily see how efficiently the drive unit is coupling to the transmission line. So the more efficient this coupling is, the more efficient the cabinet is behaving, the more output we will get for a given drive unit displacement. So it's a really nice metric to see that if a tweak we're making is improving the efficiency of the speaker, because there's many times where you might have more measured SPL from a speaker than a previous design, but actually it's just because the drive units, for whatever reason, is moving a lot more, and actually the overall system is less efficient and might run out of headroom earlier. So this is a really quick way of objectively saying, well, this system is more efficient than another. That's a really, really useful metric that we've developed. We use an awful lot these days. So
On a
that's
side note, the really nice thing about developing speakers with transmission line base loading is that when you get towards kind of the latter stages of design, you can play around with some of the transmission line geometry and absorption, and you can tune the metric like you're looking at on the excursion efficiency in front of you to make the speaker capable of higher SPLs with higher headroom, but perhaps with a little bit less low end extension, or you can tune it to have a little bit more of that low end extension at the expense of headroom. So you've got kind of like this nice last minute ability to tune the product slightly.
No, I think, yeah, we'll go into more detail in some of those ways we can tune it in a bit, but you're absolutely right. Like there are multiple degrees of freedom in transmission line speaker design, I think more so than in a lot of others, where we can have massive impacts on the whole speaker's performance with quite unassuming tweaks to various parameters within inside the design, like foam placement and things like that. Yeah, should we move on?
Sure.
So this is just a fun little video of just running a sweep, doing an excursion efficiency measurement within our semi-anechoic chamber of a 2523 speaker, which happened to be what I had to hand.
So yeah, you can see the showing the laser, which is pointed directly at the surface of the drive unit cone, measuring the distance that cone is measuring and displacement.
Yep, and then at the other end we've got our nice B&K microphone near field to the vent, and that'll be measuring the acoustic output from the vent, and then inside Clipple it correlates the two measurements and yeah, it gets a metric of acoustic output for a given driver displacement. Obviously I was impatient and didn't wait for the measurement to display there. Sorry about that. So a few things about measurements. Obviously, similar to simulations, you need to make sure that your measurement is valid. It's easy to point a microphone at any point of a speaker and say, oh, that's the sound the speaker's outputting, and trust it completely. And you can be completely wildly inaccurate in that assertion. You need to make sure that you're measuring the speaker in the correct environment. We don't want to be, well, usually, unless you're doing system tuning, you don't want to measure the room that the speaker's in. You don't want to measure the room's response to that speaker. You want to generally have a measure of the direct sound produced by that speaker at the measurement location. Generally, you can only measure at a single location in space, so you have to take that into account at a single time. But you don't want anything interacting with that. So obviously, the easiest way of achieving that is to measure inside an anechoic chamber. At PMC, we are a small company. Unfortunately, we don't have access to a full anechoic chamber ourselves. We've got semi-anechoic, which is anechoic down to about 200 hertz-ish, and is suitable for most of our needs. If we do need to do further accurate measurements of the low frequency part of our speakers, we could go outside and do ground plane measurements and things like that, which is another very accurate way of removing the room because you have no room. You have to make sure that you're measuring appropriate things for what you're trying to find out. There's no point running a super high frequency sweep on a woofer if you're trying to measure how its low frequency output behaves. And there's also, you need to make sure that you're measuring in the right location and getting the appropriate information. Seems like a small and obvious point, but it can be quite easy to waste an awful lot of time taking a whole suite of measurements that are irrelevant to what you're trying to find out. So yeah, we've got a whole load of we've sort of gone through and set up a whole range of measurements for different purposes that we go through and make sure that they're really repeatable. So I'm doing transmission line development, I want to get a near field driver measurement, I want to get near field vent measurement, I want impedance measurement, and I want maybe half meter and 1 meter on axis measurement to see how it's summing. And the main thing is that you do these measurements in exactly the same way every time, so that the next time you do that measurement on the next iteration of the product, you can directly compare those measured results and that they are still valid compared to each other, because there's no point comparing two measurements that were measured in different circumstances at a different point of the room that might have a slightly different interaction, because that will blur the actual measured differences between the speakers. So it seems sort of a bit boring to focus on this so much, but it's so critical to being able to trust that you have a genuine understanding of how the speaker's behaving.
Yeah, also it is boring when you have to, I mean, like particularly if we're hiring out the big anechoic and you know, you're taking all day to set up a suite of measurements. That's not interesting. You're just moving the mic around all day and remeasuring, right?
Yeah, no, exactly. So that image was taken at Salford's anechoic chamber, where I was a student, and yeah, it's a very nice facility to rent out occasionally, and we'd love to have one ourselves, but I don't know how much that cost when it was built, but several £1 million, I think, and seems somewhat extravagant for a company of our size. But as I say, it's amazing what you can learn from inside a semi-anechoic and outdoors. So yeah, as Ollie mentioned, some of the things that we can tune inside a transmission line that are super critical to its performance. One of the key ones is the acoustic absorption that we place inside the cabinets. So I'm not sure how many years ago that development project was done, but we've sort of come to a design of foam that we use on most of our products. It's very highly specified in terms of density, pore density, or the fact that pores are open, not closed pores, and various other parameters that we need to have it function as we want. And that gives a really good balance between high frequency absorption, low frequency damping, and without losing too much energy at low frequencies through the foam. Now, through the development process of any of our speakers, we will spend quite an absurd amount of time sometimes going through, I mean, I don't know how many the most iterations have gone through it. I've definitely got to iteration 30 or 40 before on foam sets. So you'll print out, as you can see in this image, you print out a design of the cabinet and just draw on foam sets that you're going to try, go through them, measure, listen, and take notes on each one to make sure that you're working towards the sort of optimal solution. Now, it's not all trial and error. We have, just through experience, you get a very good idea of what's likely to work in a given cabinet and a given drive unit. And again, it comes back to this idea that some transmission lines are sort of very highly tuned enclosures, and some drive unit sets of parameters will prefer a more restrictive transmission line with more foam in it. Some will prefer a more open line with less high frequency absorption, but maybe with a stronger taper, and they'll behave better in those sort of designs. So yeah, we have an idea of what might work, but then you go through a huge development process of trying different profiles.
Yeah.
It's different locations.
It's an iterative process, like you were saying, isn't it, Toby? And that's why I think you want to show like these sketches that we have. We number them up and then make sure that we've got the full suite of measurements allocated to each of these numbers, because when you've got maybe sort of 20 or 30 different variations, it's real easy to then get a little bit lost over what you're trying to achieve, which one sounds better, which ones measure better. And these are pretty neat, let's face it. Normally what we've got on these is like highlighters and scribbled notes coming out where we've added an extra pad, and normally we're looking at, this is like foam set 37, final, really final, this is definitely the last one, this is the best one, along with sort of all of the listening notes to go with it. But the more detail, the more notes we take, the better the process.
I mean, it is astonishing just how much moving a single pad of foam can change the performance of the speaker, though. I mean, I don't know if you can even see the difference between the two variations on the left there, 4 and 5, but there's one pad about that long, which is about that thick, being placed at the bottom of the speaker on the second option. But I can assure you that performed very differently to the iteration before it. That introduced an extra restriction at the end of the transmission line. It reduced the vent output, didn't change much the high frequency absorption, but it just lost efficiency in the line. But in another set of circumstances with another drive unit, it might have benefited the transmission line. So it's worth trying. So yeah, it's a long process, but worth doing. So moving on from, once we've finalised the foam set, the transmission line design, the woofer design and development, the next stage would be mid and high frequency drivers. So we will sample many options from different suppliers, different OEM suppliers. We have a couple that we also manufacture in-house, which we will obviously try and look at. We try to at least customize any part that we do buy in to make sure that it's suits our requirements exactly. So there's a lot of modification of drive units that happens, be it cosmetic or performance based. Certainly with mid and high frequency drivers, a lot of time is spent on waveguide design, faceplate design, things like that. Recently in mid ranges, we've designed what you can see here, which is the PMC 55 2-inch mid-range dome mid-range driver, and so that was quite a large project in itself. So it's a very odd waveguide design which we developed. We're looking at rear chambers and changing the pole piece design and things like that to get optimal performance for what we needed. So for that will be a lot of custom parts, a lot of prototype parts. We'll move on shortly to how we do the prototyping. And yeah, then we'll verify and make sure it's all good. So for prototyping in-house, obviously we make use of 3D printers. I'm sure most people do these days, but yeah, it's so helpful. I mean, you go back 10, 15 years to get a prototype waveguide, you'd be either doing it out of plasticine, which I believe was done very extensively back in the day, or you would be getting a turned metal part made or a turned wood part made at extreme cost and quite a lot of time as well, which delays your prototyping. Whereas now, in a couple of hours, we can print out multiple options for various waveguides or things like that, and lets us try these ideas much more quickly and iterate on them much more rapidly, which is so beneficial to allowing us to make new things. Also, it lets us try shapes that would just be really difficult to make. So if we go back to that previous slide, the flange on the front of that waveguide, I don't know how expensive that would have been to get prototyped on, say, a 3-axis CNC mill, but it would have been a lot of money to get one prototype made, whereas we could knock off 5-6 prototypes of slight variations and very rapidly for very little money. So it's enormously beneficial. And it's not just for tweeters that we can do this. So here's some examples. We've 3D printed entire transmission line cabinets. That one there is just for verification that it will perform as intended once you 3D print a transmission line cabinet, and it's surprisingly close to MDF actually if you get the density of the infill correctly. But that again lets us try out new ideas with more complex geometries than otherwise we would be able to. And other things like a laminar vent, as you see on the right hand side, which is our sort of airflow optimizing vent that we've developed. And so other things, all parts that get added to a speaker and the entire speaker cabinet itself, we can now rapidly prototype like this, and it's very helpful. So during mid-range and high-frequency driver development, we come back around to one of the PMC core concepts, which is we like wide directivity and smooth directivity from our loudspeakers. It's so important to getting a natural neutral sound from a loudspeaker. I think it sometimes gets forgotten that you don't just hear the sound that comes from a loudspeaker directly to your ears. You're hearing all the sound that gets radiated in all directions, then reverberating around your room, and eventually finding its way back to your ears. And we think it's so important that the sound that is reflected off a wall, certainly the first reflections off a wall, don't have a really peculiar frequency response, a very different frequency response to the on-axis sound that you're directly hearing. I think we find that your ears pick up a very modified version of a delayed signal from a sidewall as quite a strange anomaly to the sound, which can really affect how you're perceiving space and imaging in 3D space of the sound field. So yeah, a large part of the waveguide design that we're going through, and certainly in high frequency drivers, is measuring at all points in space in front of it. So this here is a overlay of multiple measurements up to 90 degrees off axis overlaid. So you can see that is a fairly constant directivity drive unit, which means that as you go off axis, the overall level drops a little bit, but the shape of the response doesn't change much. So that would mean that the off-axis sound might be quieter, but it has the same tonal balance as the on-axis sound, which is something that is very beneficial. So if we move onwards again, that can then be displayed as a polar plot like this. So it's just another way of visualizing that same data, which makes it very easy to see sort of in space around that driver, how is it projecting sound. So yeah, this slide is just showing a cutaway and exploded diagram of that same PMC 55 mid-range driver. So just a interesting visual of, I believe this was handed off to manufacturing. That one would have been. Yeah, onto crossover development. So another enormous task to overcome as part of the development of the speaker, and probably arguably the most important. I think I always say that you can take the best cabinet design, the best drive unit designs, and make the most disgusting sounding loudspeaker with a bad crossover. It's the one way you can ruin every other thing that you've done in the loudspeaker development process. So getting it right is so important. So we would generally start with either a quick DSP crossover, so run the speaker as an active speaker, and set up a crossover in DSP to give us a vague idea of what sort of crossover points might be suitable for the drive units and give good directivity and things like that. We'll then move over to taking those active crossovers and you sort of targeting them a little bit in crossover design simulations using very accurate measurements of the drive units in the cabinet and inputting that to a simulation software and inputting passive components into that, seeing how it comes out. Then we will produce some prototypes of that initial simulation and then start voicing from there, where you're making small iterative changes, measuring listening against reference speakers, and sort of gradually inching towards the exact sound that you want and the highest performance you can get. So it's just this slide's just sort of in case you're coming from outside of the loudspeaker industry, just the vague ideas of what crossover does. So every drive unit in a loudspeaker is optimized to play a certain bandwidth of frequencies. So a low frequency driver, a large bass driver, although it might have a response up at 10 kilohertz, at that frequency, it will almost certainly be suffering from extreme cone breakup modes, where the cone starts flexing and twisting and bending, which causes distortion and changes in the response, or just lots of anomalies. And also its dispersion massively narrowing just because the diameter of the driver means it can't produce a wide sound field at high frequencies. Opposite to that, a tweeter, a high frequency driver, you try and play 20 hertz at large output levels from a tweeter, it will explode very quickly. So crossover's role is to only send the frequency bands to each drive unit that they are happy playing and perform well whilst playing, and to manage the phase and frequency relationships between these to make sure they work optimally. There's two forms of crossover. There's a passive crossover, which uses passive components, doesn't have any power requirements. You would feed it with a single amplified signal, and then it splits using inductors, capacitors, and resistors. It will split that signal into appropriate signals for individual drivers. It gives you the option to use your own amplifiers and your own outboard equipment that you might want to use and to upgrade your system down the line, which is nice. There are issues with passive crossovers in that you can get inductors coupling to each other, causing the signal from one driver to leap over to the signal to another driver, which is a very odd phenomenon. You can get poor electrical damping of the drivers, because it's going through essentially like a sponge electrically. So as the components react in different ways to the signal, so you don't get good direct control from the amplifier to the drive units, and you can't implement limiters and things like that for driver protection. So there are.
Apart from that, they're great.
Yes, but they are, they are by far and away the most common type of crossover you see, because they also, if done well, you can mitigate almost all of those issues and can sound excellent. However, if the customer wants it and the budget allows, an active crossover can be a preferred option, which is where a signal level crossover is implemented. So it can be analog or digital, but the crossover is done before the power amplifier. So you have an individual power amplifier channel for every drive unit, and the signal that's fed to that amplifier has already been processed to band limit it. So this gives you massive control over the individual drive units, because there's a direct coupling between the amplifier and the driver. You can, certainly if in DSP crossovers, do much more complex filter design very easily and cheaply. You can do time alignment and things like that. And you can also integrate limiters and things like that to make sure that the drivers don't go bang when people turn the volume up too much, which is great for studio use because people do like to play it loud sometimes.
Yeah, I think it's fair to say that we see like a greater focus on active crossovers for the studio products and passive crossovers for our hi-fi products.
Yeah,
and it's finding the right solution, which is right for each individual application.
totally. So once, and this stage of the aesthetic design is kind of done in tandem with everything else because as I was doing right at the start, we're always doing design concept sketches, renders, and as you're building up simulations, the simulation has to be done with a 3D model, and so there's always a working model of what the speaker's looking like, what it's going, the direction it's heading. So this is constantly being iterated on by various people along the development process. But yeah, we'll consult with marketing and sales teams to see sort of what design aesthetic they would prefer and what they think is going to be appropriate for that market. We'll look at what the other market, what other people in the market are doing at the moment and what interior design trends are happening at the moment to see what's likely to fit with people's homes or studios. We'll create, as we approach a final design, we'll start creating more high quality renders like you see at the bottom of the screen there. And then obviously the pre-production units, once we've got final sign off of the design, will be produced to the final aesthetic quality and things like that. After that, it's final sign off of the speaker because we've gone through the whole development process, which is fun. So this is where Ollie comes back in and goes through that.
Yeah, thanks. Yeah, so I think Toby's walked us through like the in-depth steps of the product development. We'll then get together as a team and compare what we've designed against product design spec and sign off on it. And we'll have a meeting and a sign-off document to couple with it. And I've just thrown in here the next step, going into pre-production, where we are producing a small batch of the product and getting ourselves ready for manufacturing. We will have checklists like this, which anyone is allowed to scribble on from our technical production assemblers who are very much trying out what we've done in terms of build guides, test guides, jigs and fixtures, and making sure that our bill of material is correct. We'll have an out-of-box experience session to make sure that everything down to the packaging fits and feels right. And then we'll start evaluating our pricing and costs and noting down anything from any design modifications that might come from the practical element of initial assembly. So yeah, like I said, it'll be a small batch build, but representative of what we're going to be going into with main production. Trying out those test processes and assembly guides so that when we go into production, the products are well built and tested for reliability. Speaking of which, this is a shot of one of the heat and humidity test chambers. That is one of many tools that can be used as part of the test and verification stage to ensure that the product is going to be reliable and live out as long a life as possible. So we'll do testing to ISO specifications for consumer electronics, and if needs be, make small adjustments to the design as we go. Then we've got things like product release information. We start to look at what we're going to publish about our products, what measurements, what spec sheets should we be publishing, which will help people to choose what product is best for them. It's kind of there's a bit of difficulty with every company doing this differently. I think that's beyond just the audio world. I think that's with any product design and manufacturer. We try and choose carefully to not cause confusion with people comparing specs from different companies that might not really be representative because of the way they're measured or the way that any specification can be manipulated. So example specifications for some of our new pro products would be publishing directivity plots, as we feel that that's an important metric, along with things like max and peak SPL, always important, and is a reasonably helpful measurement to help you choose what size speaker fits what size acoustic space, what size studio. And then we want to go to launch, release the products, possibly at a trade show, organizing photography and other materials around how we're going to sell and market the products. It's nice to be able to utilize sort of a global trade show to synchronize the launch and get the product information out there into multiple markets all at the same time. And then the final stages are rolling into main production. And I'm sure, like every company, you carry forward a few little difficulties into that first production run. And there's quite a lot of engineering emphasis to ensure that goes as smoothly as possible. And then the final thing, which is kind of critical in any project, is a wash-up meeting where we get together and we review the project from start to end, what went well, what didn't, so we learn and make sure the next one is even better. And I think at that stage, it's probably best if we end there. And I thank Mike and Sue and Neil and AES again for giving us the time to talk.
Yeah, thanks very much.
Ollie, Toby, thank you very much indeed for a tour de force in loudspeaker manufacturing. That's been absolutely fascinating. I'm sure there's lots and lots of questions. Just to reiterate, we will, I think, stay in the chat room in the webinar and take questions. I guess we have to go through, Sue, and just convert people to panelists, as it were, to enable everybody to talk freely and openly, which I'm now going to try and do from here, if I can. I'm only seeing the four of us, as it were, Sue, you, Ollie, Toby, and myself. How do I get to see everybody else's?
I'll go through them.
You'll go through them. Okay, thank you, Sue. Sorry, I'm not seeing that on my screen here.
While that's going on, I think there's been one question already from Konstantin. Ollie, I think is probably the best one to answer that. It's about the laser interferometry. Asks, is that related to the Xerion laser microphones?
Depends which laser thingy it was. Was it the one that we were using that we now use in-house for development, or was it the...
I think that was questioned as you were talking about the interferometry, so probably that.
Okay. I mean, I suppose actually my answer is the same to either. I have no idea. I don't know what the Xerion laser microphones are.
Yeah,
I think they're used for ultrasonic measurements, but I know not more than that about them. I've heard of them being used for sort of stress, exploring materials and that kind of thing. But yeah.
I mean, for sure, yeah. The laser that was used for the MPL technology was primarily used to measure things like displacement and vibrations on materials by pointing it directly at the vibrating surface itself. So I imagine it would have needed to be capable of venturing into like the ultrasonic kind of range. We were like very much trying to use this laser for a completely different purpose. But yeah, I don't know.
Yeah, so I'm actually, I'm the guy who asked the question. So the reason why I'm asking this is because the guy who invented these Xerion microphones went to the same university in Vienna as I did. And his first recording was something very similar to you in the audio range. He didn't record a loudspeaker, he recorded a violin playing, but the principle was exactly the same. So this looks, and it was about 10 years ago. So the time frame seems to somewhat align. So I was just interested in whether there's a connection or just two teams developing similar concepts at the same time independently.
And was it the same concept that the laser was measuring sort of refractive index of air rather than a vibration
Exactly.
off of the violin. Ah, right.
Absolutely,
Fantastic. Well,
yeah.
I mean, yeah, timeline wise, I would imagine, yeah, it would be about 10 years ago.
Yeah, that I'm sure they know each other, because it was both were done in academic contexts. So I'm sure
Well,
they
the
know
chap
each
that
other.
I was working with at NPL to do the research had a great, very memorable name. He was Ian Butterworth. I always remember that as his
Right.
surname has a link to the the audio world. I'll check in with him and see if there was ever any sort of collaboration between the NPL and anyone else.
All right. Interesting.
Thanks, Ollie.
Thank
Thanks,
you.
Konstantin. Question from Susan Parker, who says, how was PMC originally funded as a startup in the early 1990s?
Ah, great question. So yeah, Dad was at the BBC until 1991, and essentially got to a point where he was managing outside broadcast studios, although I feel like Mike might correct me on this exactly. And he had been working in R&D and was, you know, now sort of fairly high up manager, earning good money. And I always kind of think when I listen to him talk about this or reflects on it, it's like beautifully arrogant that he thought, yeah, no, we can just definitely do this better. But he had this passion that he could innovate and use a multitude of different technologies to produce better speakers. Him and Adrian, I think the story is, went to the bank and borrowed £50,000 each, quit their jobs, and then I think within maybe 2 months had spent every single penny, and found themselves having developed kind of one speaker, but I think a little panicked to very quickly develop a range of other products that they could then sell out into the studio world. And yeah, those first few years, I think there's a lot of difficult times for our family. Lots of build of the initial products in our house, and yeah, funding was difficult. It's a challenge. I mean, I can't imagine what it would be like today.
Be interesting thinking about how much. Sorry,
I was going to say that's. Oh, sorry, I interrupted you. That was a lot of money in 1990. £50,000 each. It was quite a commitment.
Yeah.
As I say, it'd be quite interesting to think how the initial setup costs would differ now that we do have access to things like rapid prototyping and things like that. Some of the costs could be reduced perhaps today for getting initial prototypes made, but maybe other costs would be a lot more. So it might sort of even out in the wash, who knows?
Well, I mean, I think even still back then, I can't remember what the exact amount is. You know, a large amount of that initial loan went into financing some of the test equipment that they used back then. And so like ever since the beginning, the focus was very much on investing in technology to help us design better products.
One of those things where if you get ahead on the actual technology to measure and validate your speakers, it gives you such a better chance of actually producing something worth producing.
Okay, any more questions? I certainly have one while other people are thinking. In fact, I've got lots, but I don't want to hog the show. You mentioned you know, the signature of the company, if you like, is the advanced transmission line. I suppose it's a two-part question, really. Would you ever depart from that, or have you ever considered departing from that? What about its how do you see that as a compromise? You obviously, Toby's shaking his head to the first part, which is a straight answer. So you must obviously believe that it's the right solution to the problem. I mean, in the smorgasbord of compromises that the loudspeaker is, and I think that's what makes it to me such a fascinating beast. So many different things going on in the different domains. How do you see the compromises between things like, for example, it's a fourth order response, correct me if I'm wrong, Okay, you're going to talk me through that.
So
and the transient response of a transmission line, it's a resonant thing, isn't it? Or is it, do you heavily damp it? Yeah, how do you see all of that stuff?
Before Toby goes off into detail on that, which I can tell he's about to, I think like PMC engineering, the design philosophy is not to rule out any technology because it doesn't fit with our brand or isn't something that we like the idea of. It's to try everything and to find what technological advancements there are. At the moment, for cabinet enclosure design, we're pretty satisfied that we aren't sticking with a transmission line or an advanced transmission line design because that's just what we've always done. It's because that's what we think gives a noticeable benefit in terms of performance in that area of the design. So that's why we would continue to use it. If there was another base loading technology that we find offers more benefits, I imagine we will switch to that because we are just trying to produce fantastic speakers. And that applies to everything else. I mean, we're kind of synonymous with these dome mid-range drive units, and that's not because we start out at that product design spec stage and say, right, okay, well, it's obviously going to have a dome mid-range. If we're looking for a speaker, it can be a three-way model, which gives more specificity to each of the drive units. The mid-range drive unit wants to have a wide directivity, and we're looking for low distortion. So what we inevitably always find is that a drive unit with a super low mass diaphragm, which is kind of synonymous with the dome mid-ranges, gets us there. And that's why we tend to always use them.
So back to the sort of potential downfalls of transmission lines, I suppose the obvious one is always size. And we've put an awful lot of research into how can we minimize the size of our cabinets whilst maintaining decent extension and bass response. There is always a fundamental link between the length of the transmission line and how low of a frequency it's going to resonate at and want to play. There are ways of shrinking the cross-sectional area and the overall dimensions of the cabinet significantly if you choose the correct driver and use the correct transmission line geometry. So I think there certainly are projects that would not suit a transmission line. So if we were talking about very small speakers, sort of tiny desktop or sort of soundbar size Bluetooth speaker sort of things, I think they just wouldn't suit transmission line base loading necessarily. Luckily, that's not the market that we're currently in, and for the market we're currently in, as Ollie was saying, we do tend to find that this offers the best set of compromises for what we're trying to achieve. You mentioned the order of the bass roll-off, and if you actually look at the literature from the original transmission line papers back in the 60s from like Bailey and people like that, I think it was always asserted that a true transmission line should have a second order roll-off, similar to a sealed cabinet. That's largely due to the fact that they were aiming to absorb the entire rear wave within the transmission line cabinet. So essentially it was acting like a very well damped sealed cabinet at that point, with a half wave resonance, I suppose, if it was sealed. But anyway, what we actually find with our cabinets, because we are utilizing the rear radiated sound at the end of the end of the transmission line to augment the bass response, that does add to the roll-off slope, but it's not fourth order typically. We generally find it sort of sits around 18 dB per octave, maybe a little bit lower, depending on the exact design. It very much relates back to the geometry of the line we've chosen, how tapered it is along its length, how open it is, and the drive unit, but also the amount of position of the acoustic foam we put in the transmission line. The more foam we put in it, the more damping we achieve, and the slower the bass roll-off actually becomes. It's all to do with how broad the overall transmission line resonance is. So it tends to be quite a low Q resonance because of all the foam. The lower Q that resonance become, the more the output from the vent stays in phase over a wide frequency with the bass driver. So obviously, if you have a very high Q resonance, the phase of the vent output is suddenly going to change from the output from the bass drive, which is why you get that high order roll off in some designs. Because we've ended up with quite a low Q resonance, there's sort of phase coherency between the base driver and the vent output over quite a wide frequency range. So as you go down in frequency, it's still actually summing quite well, so you don't get such a steep roll off at the base frequencies.
No, lovely, thank you. So in the parlance of group delay, if you like, you're somewhere between a sealed box and a
exactly, yeah,
vented enclosure, something like that. And presumably the time domain response likewise is a little bit more oscillatory and higher order than a sealed box, but not
fractionally more, yes. But again, it's incredibly well damped. It is a resonance system, absolutely, but it's a very low Q resonance system, so it does behave itself very well. As I think a lot of the side benefits that often get forgotten as well. It's the primary function of a transmission line is to augment the base frequencies, but I think what gets forgotten about is that we're also, because we don't want mid and high frequencies exiting the vent, because there would be very out of phase with the front driver's radiation, we're absorbing them quite resistively inside the transmission line, and that means that you don't get reflected sound from inside the cabinet coming back out through the driver cone, instead of it being sort of an empty cabinet with a tuned section. It's incredibly absorptive at high frequencies and mid frequencies. So there's a massive reduction in mid-range distortion as a result of the transmission line loading, which you sort of wouldn't necessarily consider. So part of the reason that we end up with such low distortion out of our speakers is because a lot of this unwanted mid-range and high-frequency energy that is radiating off the rear of the drive unit, the base driver, it just goes into the cabinet and disappears and doesn't come back through the cone, which otherwise would be time delayed and very much altered coming back through the driver cone. So that's quite a big benefit that I think doesn't get realised quite as much as it could or should. Pardon me.
Lovely, thank you, Toby. That's very comprehensively answered. Elena Prokofyeva has a question. She says, I like the idea of 3D printing loudspeaker components. Do you print driver cones? And you mentioned in-house drivers in your talk. So if you unpack that one a bit, perhaps.
So the very simple answer is no, we don't print driver cones. The materials that we're commonly printing in are things like ABS or PLA plastics, and also just because of the method of 3D printing, it's building up a model in layers, so you don't have a smooth sort of homogeneous part at the end of it. That has layer lines and it has breakpoints and weak points. So I think the resonant behavior of, if you tried to 3D print a drive unit cone with this technology, would be quite peculiar. I think if you think about the goals of a drive unit cone, you want it to be as light as possible and as stiff as possible generally, but also to be well damped, which is obviously at odds with the stiffness. But it would be interesting because you could probably print some quite interesting cone geometries which might mitigate some of the loss of stiffness from using a soft plastic material. But
yeah, I mean for prototyping.
Oh, for prototyping.
Causes, like trying different shapes. Because I remember doing the rapid prototyping of G-tails, and you have to wait for ages to get them through the door, and they cost fortune, like you said. Having 3D printer might help a little bit.
Yeah, I mean, you could definitely 3D print driver cones. I think like Toby was getting at is the consistency of the material that we want to use, as well as making it lightweight, doesn't really lend itself for that process, like for manufacturing. But I mean, you could also utilize like some more modern 3D printers, which would be able to print the cone and sort of flexible surround all as one piece, using a mixture of different materials, because you can print with a sort of slightly more elastic rubbery type material. You can print with a harder plastic. So yeah, it's something that could be done. It's not something that we have ventured out into, although different drive unit cone materials is something that we've experimented with.
Yeah, it's certainly something to think about. Certainly as an aesthetic sort of visual guide, and if we were trying something new, it'd be interesting to try it, to get an idea.
And then the other bit that you were talking about is you mentioned in-house drivers in your talk. So we are talking about in-house manufacturing and in-house sort of ground-up development. Most of the drive units that we are producing in our speakers are designed in-house, either fully or to some degree. and it's the manufacturing which is more not in-house, that we don't do ourselves. There are some key designs that we do the entire drive unit manufacturing, but they're the more sort of high-end and mid-range drive units, which you see in all of our big studio products, and the technology of which we're particularly proud of, and we want to keep all of that in-house.
Yeah, it does hurt somewhat because we're obviously there's a couple of other large dome mid-range drivers on the market which sometimes look quite similar to ours and often get confused for ours. It can be somewhat upsetting when people, oh, it's just a such and such driver, isn't it? No, it's not. It's our own one that we make ourselves very carefully. So yeah, it's we are quite proud of the amount of care and effort that goes into the ones that we do fully build in-house. It's a long process.
Rupert, I can't forget to just quickly read out your theme tune suggestion when I was chatting at the start of this. It should definitely be Everything Louder Than Everything Else by Meatloaf. That was genius.
I think Rupert had a question actually anyway, so far away, Rupert.
Yeah, and for those who don't know, I was senior engineer at Maida Vale when Pete Thomas wanted to try out his BB5s. And we were evaluating a lot of different speakers for the Rock Studios at the time. And I do remember saying to him, Pete, these are the country's finest rock studios. We're evaluating serious speakers here, not something you've knocked up in your garage. But he was my boss, so they got evaluated, and the rest is history. What I wondered, Ollie, is how your experience in motorsport transferred across to loudspeakers.
I mean, it was kind of, yeah, experience before that in my mechanical engineering experience. I just learned really good, solid engineering principles, and working at a couple of really sizable engineering companies ingrained in me the importance of design for reliability, how to test, and kind of put in place a lot of the things that I was talking about today, which is the key processes for product development, which I carried forward into audio. It also taught me I didn't really like people in the motorsport engineering world, and I very much prefer all of us audio engineers. We're a much more fun group of people. I mean, there are things like sensors that I was developing for the Red Bull cars, calibrating and optimizing them, along with sort of some elements of electronics design. And then we also, I mean, Toby talked very briefly about a injection molded plastic part that we use with theory on more and more on some of our designs, which have like high excursion drive units, which cause a great amount of airflow in the cabinet. And then we're starting to dip into mechanical and aerodynamic engineering principles. I was able to help apply that when we were developing those products. But I think it was just really kind of like probably working at the BBC is like really ingrained into you, these core engineering principles, so that whether you're designing or testing, you can do it with your eyes closed, and you just you know the importance of getting it right and the consequences of not. And I think that means that you can develop better products faster.
I think you've been very good at instilling that sort of ethos in everyone at PMC as well, which is quite beneficial for all of us, really. We all work with the same goal in mind and the same mindset of making sure that things are done correctly and sort of having integrity with what you're doing in engineering.
Great, thanks, Rupert. Andrea Salamoni. Andrea, you have a question about crossovers, I believe. If you want to unmute.
Yes, I actually, the question is, if other than the crossover themselves, do you use any DSP algorithm in your loudspeakers to improve the acoustic performance?
Yeah, and the short answer is yes. In most of our active products, the crossover, we have moved over to a digital signal processing to control the crossover slopes, the filters, and also add in things like Toby was talking about earlier. We've added limiting control and sort of parametric EQ to allow a little bit of drive unit correction in terms of our own custom algorithms, although the control of the DSP and the code for that, we write that and we optimize it, and that's completely unique to us. You might be talking about sort of a different type of custom algorithm to develop a different filter characteristic, which I suppose we probably haven't ventured too far into.
Okay, fair enough. Thank you.
But yeah, I mean, DSP as a technology that was kind of limited by what was achievable with the semiconductor components. Then there was quite a lot of D2A and A to D in the signal flow, and I think it took a while before distortion amongst other characteristics were measurably low enough for it to be viable. But yeah, like I was saying, now we use DSP as the crossover platform in pretty much all of our active products.
It's quite interesting. I think a lot of people these days consider active speakers to be synonymous with DSP and think it must be have a DSP crossover to be an active speaker. But a lot of our main monitors going back, well, a lot of our active speakers and studio products going back all the way to the beginning of the company use analog active crossover. So it's very much the same circuit topology that you might see in a passive crossover, but at line level voltages and much sort of surface mount components and things like that. But you still get such much of the benefits from an active system, like the better amplifier control and, over the drivers and things like that, even though it's an analog system rather than DSP based. But yeah, it very much has moved over to DSP systems now, just because it gives us so much flexibility with what we can do, and being able to time align things is a huge benefit now. Sort of having processors that have memory and can store the audio signal for the drivers and allow you to really start optimizing sort of the phase response and things like that of your loudspeakers is a big benefit that we've recently been able to use.
That's great. Thank you very much.
Do we have any further questions, either in the Q&A or just raise your hand, Matthew Ward?
Hi, it's a really brief question, but in your 882 product range, you mentioned the web app and that's all really good, and the DSP integrated in there now, which I found really useful. I was wondering if there was any science or what your thought process was around the number of bands of parametric EQ you make available for room correction in that product.
Yeah, so yeah, thanks for the question. In the sound align software, which controls the DSP within that product, and allows you to apply a couple of shelving filters, as well as it's a 5-band parametric EQ. It's been asked a couple of times from different people about whether that 5-band is there for a reason. Why isn't it like 20, or why isn't it 1? And the reason that is there is exactly as you pointed out, for a degree of room correction, which can be done with frequency response with parametric EQs. The reason we limited it to 5 is that when we've been spending a lot of time in high-end recording studios calibrating systems and aligning them to the room and applying these EQs, that's the limit of what we find is useful. As you use more and more, you can smooth out the frequency response of speakers in a room. You can do it well in one particular place, but as you move around, it doesn't work so well, and you definitely start to hear the phase characteristics of the filters. So the approach for sort of the room correction and the limitation of just having 5 PEQs is to try and set a limit, so you don't kind of get carried away with trying to smooth out very small narrow band anomalies in a frequency response, which doesn't end up with a more natural or accurate sound in the room. If that helps.
Sounds like that's answer the
No,
question?
that's perfect, and I don't disagree. There are, various approaches that various organisations take.
Yeah, I mean, and with a multitude of kind of different automatic room correction programs and softwares, if you go through, they do a lot of things right. You can program a computer to make some good judgment calls on what parametrics you can use to try and smooth out general frequency anomalies. But normally, if you go back in and sort of turn off a few of the extras that are thrown in, which are really high Q, narrowband, high order, or high level parametrics, it's normally best just to leave those. Often that's being picked up by a microphone measuring something in the room, which isn't correctable, like I said, by simply applying a parametric type filter.
I think that's a really good point. This goes back to what I was saying in the talk about validating that your measurement is actually the truth. And a frequency response measurement taken from a single spot in your room, or even average over a small area of your room, really isn't giving you the whole picture of how your room responds. Also, it's not giving you the picture of how your room responds over a certain window of time. The frequency response will be taken over a certain measurement time window, which is usually sort of maybe 100 milliseconds or so if you've gated it. But rooms have reverberation times in the order of half a second, a second, if it's that's a fairly well treated room. And your measurement either is ignoring a lot of that acoustic effect that's happening around you, or it's trying to correct or something like that. So you often find that you're correcting for things that you are hearing, things that you can't hear, or things that you are measuring but wouldn't hear. And I'm not explaining it very well, but it's very easy to end up overcorrecting for a measurement that isn't necessarily giving you the full picture of what you're hearing. So you end up getting a very pretty picture on a graph with lots of EQs that you get a lovely flat response, but actually what you're hearing from the room response, if you either change your measurement settings or move your microphone a few feet, is quite catastrophic and can be far worse than just leaving a speaker with a slightly more slightly less flat measured response at that point in the room. It's a very easy pitfall to fall into of over EQing a system. So yeah, as Ollie said, it's good to encourage people against falling down that hole if possible.
I think we've all probably heard room EQs at hi-fi shows in the early days of it that sounded pretty ghastly as a result of over-treatment. And I'm always mindful of Floyd Toole's thing of one's ears adapting to the listening space. If you went into a church and it sounded completely anechoic by some weird field synthesis thing, you would think it was very, very strange indeed.
It's quite right. It's a similar thing to if we go back to why we really focus on wide driver dispersion, because your ears do adapt to a room. So you might have a little bit of absorption on the walls or something like that, or diffusion. So your ears get used to that and expect a certain behavior from that room. So if your loudspeaker is not allowing the room to behave in that way by projecting a sort of very unusual frequency response off to the walls, we have a certain expectation with our ears that a reflected sound should sound similar to, or should have the room's transfer function overlaid of it on just the original signal that you're hearing. But if that signal has been then filtered again by the speaker having a very peculiar off-axis response, it does sound wrong to us in that room. And that's why if you have wildly a badly behaved off-axis response from a speaker, it can sound so unnatural and fresh the soundstage, because we are listening through the room quite well. Our ears are sort of tuned to what the room should sound like. But the speaker then isn't allowing it to sound natural, how normal sound source should sound in that room.
We've got a slightly different question just popped up in Q&A from anonymous attendee. I don't know who that is and whether you've got a microphone and you want to unmute and ask the question yourself. I'll ask it anyway, and then if you do have a mic, you can always come back in. What equipment do you use for testing on the production line, and what tolerances do you usually work to? I guess that's production QA.
Yeah, definitely. So the test equipment on production line is we have automated audio analyzers. which will be used alongside a signal generator and a variety of test tracks. And pretty much for every speaker we make, we'll be using these pieces of equipment to validate that the speaker has been assembled correctly, rub and buzz, that there is no rub and buzz, and yeah, typically we'll measure things like frequency response, which gives us a good idea of whether everything is within tolerance. And those tolerances, particularly like the frequency response measurements, we divide into like a narrowband peak, upper and lower limit, and an average level. So levels wise, every single speaker we're working to approximate limits of about half a dB at the extents we want the overall sensitivity of our speakers to be incredibly well matched. The limits are slightly larger for sort of small band peaks within the response.
Yeah, I think what you touched on there, which is super important, is actually the listening part of the test. So as you say, there's quite comprehensive measurement of every loudspeaker that goes out of the doors, and that's all recorded against the serial number of those products. But also all of our production staff are very highly trained in listening tests. We go through them and make sure that they're all comfortable with the specific listening procedures that we want them to do. And they all have quite excellent hearing, and all frankly very keen on music pretty much. There's several extreme audiophiles amongst our production assemblers. But yeah, as I said, we go through a set of reference recordings for every loudspeaker that goes out the door. There's a reference speech recording from the BBC, which we use, and then there's a couple of tracks of music of different styles that also gets listened to again, and this is always done against the production reference speaker. So as we finish the development process for a loudspeaker, we produce an absolute reference pair, which is exactly how we want them to be. And then every speaker that comes off the line gets listened to and measured against one of that pair of speakers to make sure it sounds exactly the same. So yeah, that's
well said. I guess I just add a little bit more details to that, which was, we were talking earlier about like direct sound, memory radiated sound, and off-axis sound. When I'm talking about us using things like a audio analyzer to measure a frequency response, that is only done on axis, and as we were talking about, there's like limitations to that. And so you could very well find a pair of speakers that would both pass an on-axis listening, on-axis measurement via that equipment, that our production assemblers will listen to that pair of speakers and say, nah, those tweeters aren't matched. And that's because what your ear can do is pick up all of the off-axis sound and sum it all together and determine whether it is or isn't matched. If we took that pair in my example away and measured like 180 degrees of off-axis sound, we then find that they are not too well matched because the 20 degrees or 30 degrees of axis or something, and the lobing characteristic is different, and so they aren't matched across the whole sound field. So yeah, listening is super important.
Yeah.
Right, great question, thank you. I'm conscious of time. I'm very tempted to ask just one more, if I may, and then if somebody else wants to pile in, and then we really must wrap up, I think. You mentioned voicing earlier on and how important that was, and I guess in the studio market, and certainly from my BBC days, the broadcast market very much looks for consistent voicing. How do you reconcile that with the desire to incrementally develop the product? Do you is there a tension between changing something because you can improve it versus keeping the voicing the same, or is the voicing really more, how can I put it, more subtle than that, more to do with the mid-range response and aspects that don't change perhaps dramatically from one development to the next? How do you square that circle?
Yeah, kind of the question also is, what even is voicing? What does that mean? How do you technically define that and go about it? And how is that in many ways different to crossover development that Toby was talking about earlier? Yeah, I mean, I think if you find a way to produce sound more accurately, which then doesn't fall in line with the way that you would voice a speaker, I think that probably is a bit of a red flag that something has gone awry and has gone gone wrong, and that's when I think I would be referring to lots of different reference models during product development and trying to figure out what is right and what is wrong, particularly if it's something that you're picking up through listening testing. But yeah, the voicing process is a key one, and I think that's what we would use to describe many of the elements of crossover development at a later stage, rather than like big changes or the small changes to fine tune the last bit of speaker design.
In terms of the scale of changes that you're making, when we at the point of where I would consider it voicing, you've already got the frequency response to be pretty close to a neutral frequency response. It's measuring within a certain band of where you would expect it to be. The voicing really is you're looking at very, very small differences in the measured response, or on the order of 0.2 dB sometimes, and it's tiny changes that you're incrementally making to really gradually nudge the output of the speaker to sounding a little bit more how you want it to. So in terms of it being a neutral or accurate speaker, you're sort of already mostly there from the initial crossover development work, and the fine tuning, the voicing really comes through tiny subtle changes that they are quite perceptible and do, yeah, that you can clearly hear the changes that you're making. But I think if you went away for 2 days, came back and listened to that speaker on its own, any of those iterations of the voicing, you'd probably say that's still quite a neutral speaker and quite an accurate speaker. It's just you are making these fine tuning adjustments to bring it closer to exactly how it should sound, and it changes things like usually you start listening in stereo around the voicing stage as well, where you start hearing changes in the way it projects sound in width and space and depth, because you're changing subtle interactions between the drive units around the crossover frequencies. So yeah, you're slightly changing the phase behavior of the driver or something like that, so they might sound slightly different and give a slightly better vocal projection or something like that. It ends up being very fine adjustments though.
Okay, thank you. Yeah, great. One more from Elena. Elena, quickly. You're muted if you're
yeah, it's my mic. Yeah, so you mentioned like I just listened to your answer with the question before. You mentioned that sometimes you could get to the answer from production line saying, sorry, it's not matching. Do you actually do this exercise of matching the units for pairs?
Yes.
Like if you want to do the best ever pair, you will need to listen to both of them and make sure that they sound as a pair, not necessarily exactly the same, but as a pair. For
sure. The pair matching is performed on every single pair of speakers we make, and that's one of the key processes that we go through, key skill that the production engineers have that make our products fantastically well matched. And of course we document that at every stage, so we know exactly.
Is it listening or through measurements?
Say again?
Is it through listening or through measurements?
Well, I mean, like most things, it's definitely a mixture of both. So measurements wise, I was saying that we would be performing like a frequency response measurement. However, it's certainly fairly limited because it's only on axis, and so it will only capture certain anomalies, and certain differences between the drive units, which your ears might pick up others, or it might pick up something that you might have missed from listening. So you kind of need to do both hand in hand. In terms of like pair matching between our speakers, it's normally the higher frequency and mid-range drive units, and that kind of comes down to the intricacies of manufacturing and the consistency we have. Every drive unit that we manufacture in-house or that's produced by a key supplier for us has already gone through a certain degree of pair matching or matching within to like a tolerance band, which is pretty tight. So a lot of the drive units that we are fitting into the final speaker enclosure are all within such a tight matching set of tolerances that there isn't so much of a sort of like a need to swap out drive units, but that would happen on things like mid-ranges and high frequencies if anything's picked up on final test.
Certainly one of the BBC requirements I recall was to, and Rupert will remember, will correct me if it's still the case, was that you were able to substitute any speaker off the shelf for another one of identical model, and in theory there shouldn't be a difference. There shouldn't be a need to match serial numbered pairs or anything. I don't know whether that's still the case.
It certainly was when I left the BBC, but that is about 8 years ago now, because, yeah, obviously if you've got a live program on the air or about to go on the air and one speaker packs up, you don't want to have to replace two. You haven't got the time.
Exactly. And that's what I was coming back to. So if you take any two of sort of PMC speaker from any kind of production batch, they'll be matched to within whatever that tolerance is, which is the tolerance of all of the components, which we want to make sure within that sort of that final 10% anyway. So you could sort of like say, oh yeah, they're all about 3/4 of a dB matched. However, as they roll off the production line, as we manufacture in pairs, we then have the opportunity to refine that and tighten that tolerance even further. But yeah, I know what you're saying, Rupert. And yeah, you want to have confidence that you've got that storeroom with 20 spares and that they're all identical and you can sub one in.
Yeah, I mean, in terms of exact pair matching, as you say, there's a broad tolerance for all of the products, which means that they all sound very, very close to each other. But in terms of tightening that down for an exact pair, it goes quite neurotic, really. We get down to component level tolerance bands for crossovers, where obviously there's tolerances on passive components for crossovers, but there might be a 5% crossover component, or it might be a 2% tolerance. We batch test all of every single crossover component that comes through the door and put it into tolerance bands of like either plus or minus 1%, plus 2%, plus 3%, plus 4%, or minus that number of percents up to a limit of we won't use that component anymore. And then we record on the crossover notes as it's going through production that it's got only components of that tolerance band. So if that crossover ever comes back to us for repair or anything like that, we can match the exact tolerance of the components used on that crossover to what was used in the initial production. And obviously a pair of speakers will only be built with the same tolerance components. So you can ensure that the crossover is exactly matched to each other, which is, I think, quite unusual to go to that degree of intricacy with the pair matching.
Right, okay, well, if nobody else has any burning questions, and I am very mindful of the time, I'm sure we're significantly over, although who cares? It's been a fantastically interesting, real tour de force. Thank you. So many interesting questions as well. Can I express our collective thanks to Toby and to Ollie for a fascinating evening's talk. Yes, absolutely. I don't know how we do that on Zoom. I've never quite got to the point of everybody applauding, through their microphones. But thank you both so much indeed for a fascinating evening. You did mention at the start, and I know somebody will ask this, about whether slides might be made available. I don't know whether you do that through the PMC website or something like that. Is that something you might do?
Yeah, no, I think we might do a slightly edited version, but yeah, no, we'll definitely make them all available.
We'll leave that one with you.
for any fool that actually wants to look through them, we'll definitely make them available and let you know how you can access them.
Great.
Yeah. Thanks again for everyone for coming. It's been a really nice experience, and yeah, thanks for listening. Really appreciate it.
Thank you both very much. And before everybody departs, just a quick plug for our next AES lecture. We're still waiting for confirmation of the date, but the plan at the moment, it is provisional. We're going to try and go back to a hybrid format event rather than just an online event, based at the University of Leeds, which has a music and an electronics department, which exchange lectures and things for a joint course, as well as pure electronics. And it'll be our own AES UK's Jamie Angus who's going to present on some differences between the digital and analog domains in signal processing. And with Jamie being Jamie, of course, it has a creative title, True Peaks, the samples are not what they seem. So that's a tantalizing, taste of things to come, all being well, on Tuesday, April the 25th, which will be a week later than our normal third week in April slot. fit around Jamie's availability. But keep an eye on the AES UK newsletter, if you will, for the date of our next event. Join us for that if you can. Meanwhile, thanks again sincerely to Ollie and Toby again for a great evening presentation. I hope you've all enjoyed it a fraction as much as I have. It's been tremendous. Thanks again, guys, and good night to everyone.
Thanks for having us.
Good night, and
Great.
thanks for everyone for the great questions too.
Thank you. Bye.
Thank you.
Yeah, good night.
Good night all.
Thank you, bye.
It's been very informative and a lot of fun.
Cheers, Rupert.